So after having seen what a vanilla distributed file system looks like, we're going to see a couple of real file systems, the NFS file system and the AFS file system. These are very popular and continue to be used even today. First, the NFS file system. It's the network file system. It was developed by Sun Microsystem in the 1980s, and it continues to be used widely even today, both in clusters, data centers, as well as in smaller scale clusters. So here is what the NFS architecture looks like, and then I'll play it out in more detail over the next few slides. So you have the server machine, of course, and then you have multiple client machines. On the client machines, there might be multiple processes that are trying to access files. The processes execute operations with what is known as a virtual file system module. You'll notice that there is a virtual file system module also on the server side over here on the right. When a process makes a call to the virtual file system module, it then decides, depending on whether the file is local or remote, whether to relay the call to the local Unix file system or to the NFS client system. If the file is local, then the Unix file system is accessed, and that in turn accesses the local disk and then returns the information directly to the process. However, if the file is remote, if it is located on the server, then the NFS client system forwards a request to the NFS server system. This is done via typically an RPC. And then the NFS server system forwards a request to the virtual file system on the server side, which then forwards it to the Unix file system on the server side, because after all, on the server, the file is stored on local disk, and the file is then accessed from the local disk. Then the information about the file, such as a block being read, is returned on the reverse path shown by these arrows. So you'll notice a few components here: the NFS client system, the NFS server system, and the virtual file system. Let's discuss those in a little bit more detail. The NFS client system is similar to our client service that we discussed in the vanilla distributed file system. Here it is integrated with the kernel, that is with the OS, so it executes in the with kernel level privileges. Okay. It performs RPCs to the NFS server system whenever distributed file system operations are involved. The NFS server system plays the role of both the flat file service and the directory service from our vanilla distributed file system, which we discussed in the previous lecture. NFS allows mounting of files and directories. This means that clients can mount remote directories to a local directory name. So for instance, if we mount /user /edison /inventions into a local directory /user /tesla /my competitors, now user /tesla /my competitors /foo actually refers to a file user /edison /inventions /foo. Okay, so mounting doesn't copy files over. Instead, it just creates a pointer to a remote directory, so that now you can use a pseudonym, a clone name to refer to those files. It makes it convenient for users as well as processes to refer name files, name directories, and access files and directories. What about the virtual file system module, which is present on both the client side and the server side? That's the third module we saw on that figure. The virtual file system module allows processes to access files via file descriptors. Well, this should kind of surprise you at the beginning, because we discussed in the vanilla distributed file system that the vanilla distributed file system does not use file descriptors, primarily because of idempotency requirements. However, you want to use file descriptors because you want to have transparency. You want processes to be able to access local and remote files via the same API. And since local files are accessed using file descriptors, you want to support the same for remote files as well. That's what is supported by the virtual file system modules. Okay, so as far as client processes are concerned, they access local and remote files via the same API using file descriptors. But when an access is received by the virtual file system module, or the VFS module, it decides whether to route it to the local file system or to the NFS client system. And here's where the translation from file descriptors to the idempotent operations happens. Okay? So all the files, local or remote, are named uniquely using NFS file handles by the virtual file system module. The virtual file system keeps a data structure for each mounted file system. It also keeps a data structure for each file that is open. This is called a vnode data structure. Okay, here's where the translation happens. If the file is local, that is stored locally on the client machine, then the vnode points to the local disk address called the inode block. However, if the file is remote, then the vnode contains the address of the remote NFS server, so that RPCs can now be sent to that NFS server to obtain blocks of that file. Okay, so here is where this data structure, the vnode data structure maintained by the virtual file system module, is the one that does the translation between the stateful, non-idempotent file descriptors, and the stateless behavior, the idempotent operations that we really desire from the distributed file system. Now, NFS uses several optimizations, and these are the main reasons why NFS is a fast system. Server caching is one of those optimizations. It's useful for doing reads. Essentially, on the server side, you store in memory, in RAM, some of the recently accessed blocks of files and directories. Okay? Now, these might be blocks accessed by different client processes at different machines. But why does this work? Well, this works because most programs written by humans tend to have what is known as locality of access. Locality of access essentially says that if a program or a process has accessed a block in the recent past, it's likely going to be accessed in the near future again. This means that if you store that block in memory, you can then access those near future accesses to that block can be done very, very quickly. Instead of going to disk, you simply access the block from memory itself. Then when you do a write at the server, when a write is received at the server, there are two flavors in which this can be done. The first is known as a delayed write. The second is a write through. In a delayed write flavor, you do that write only in memory. You don't write it to disk immediately. Instead, periodically, say every 30 seconds, you flush it to disk. Okay, this is done, for instance, via the Unix sync operation. This is fast because the write can be now done in memory fairly quickly, but it may not be consistent. Why is it not consistent? Well, if the server crashes before it does the next sync, then any of the writes that were in memory but not yet flushed to disk might in fact be lost. If you want to be really consistent, you should use write through. Write through whenever a client write is received at the server, essentially the write is done immediately to disk before an ACK is sent to the client. This ensures the best consistency, that all the writes are in fact done durably on the server side, but it may be slow because it involves a disk seek and a disk write. What about on the client side? Well, on the client side too, you can do caching. So you don't need to cache blocks only on the server side. Clients can also cache because locality of access is also true for each process. So a client caches recently accessed blocks. Each block that is present in the cache on the client side is tagged with the time at which the cache entry was last validated, known as TC, and also TM, the time at which the block was last modified at the server. A cache entry at a given time t is said to be valid if the difference between t and tc is less than a small value of small t, or if the time at which the block was last modified at the server is the same as the timestamp that is maintained at the client. Okay, so if the second condition is true, essentially you're saying that the copy of the file or the block at the client is the same as the copy of the block at the server. But doing this second operation requires you to do an RPC to the server, which may be expensive and it may involve some amount of latency. To avoid that RPC, you give some amount of laxity to the block that you're storing and say that, hey, if the block is less than small t old, I'm going to still consider that block as being fresh. Okay, so t is known as the freshness interval. This is a compromise between consistency and efficiency. If the value of t is very, very small, essentially, say t is 0, for instance, then essentially it means that you'll never do this check. You'll always go and query the server for its timestamp. Okay, so that's the most consistent system, but it may be fairly slow. If the value of t, small t, is large, it means that you're willing to tolerate some amount of staleness for fast accesses. Typically, this value of t is set to be set adaptively by a system like Sun Solaris, sets t adaptively between 3 to 30 seconds for files and between 30 to 60 seconds for directories. When on the client side, when a block is written by the process, you do a delayed write to the server, because after all, if you have a non-zero value for small t, you're going to have stale blocks anyway, so you might as well do a delayed write, which is a more efficient form of doing a write. So that was NFS. Now let's quickly discuss AFS. We won't discuss all the design details of AFS. We'll discuss a few design details that are kind of interesting. So the name Andrew in the Andrew file system name comes from the Andrew in Andrew Carnegie and Andrew Mellon, who are the co-founders of the Carnegie Mellon University, and shouldn't be a surprise to you that AFS was in fact designed at CMU, which is how its name came about to be. It's used in many clusters today, especially in university labs. So AFS involves two very interesting design decisions, whole file serving and whole file caching. So earlier when we discussed NFS, we were talking about blocks being cached on the server side and on the client side. AFS does not deal with blocks of the file. Instead, it deals with the entire file. When a client accesses or opens a file, it is given the entire file, not just the opening block of the file. Also, when a client caches a file, it caches the entire file. It doesn't cache just a few blocks of the file. Okay, so everything is done on the file level basis rather than on a block level basis. Also on the client side, the cache is permanent, meaning that it is stored on disk. And so even if the client crashes, it can then recover and then access its cache. Why is whole file serving a good alternative? Well, you might think that the files that are very large, like gigabytes or terabytes large, would involve a lot of overhead. But in fact, these design decisions are based on measurements which showed on real file systems that showed that most file accesses are by a single user, and most files tend to be small. Okay, so this is the common case for most file accesses, and so AFS is catering to this common case over here. It's making these common cases really fast. So yes, files that are gigabytes or terabytes in size may become very slow, but those are not the common files anyway. The most common files are small and accessed by a single user, and those are made really fast by dealing with entire files rather than blocks. Also, even a client cache as large as a few hundreds of megabytes can be stored in RAM, and nowadays you can store caches that are even a few gigabytes in RAM. Also, finally, file reads are much more frequent than file writes, and so if you serve out entire files, then the reads can be served locally at the client itself rather than going to the server for blocks. Okay? And typically these reads are also sequential, so storing these files on disk is fairly efficient because now you access consecutive blocks on disk at the client side. A few more details about AFS. The client system is known as a Venus service, so every client is running a Venus daemon, and on the server side it's known as a Vice service or the Vice daemon. Reads and writes are optimistic because whenever a file is opened, the entire file is sent over to the client side. The read and write can be done on the local copy of the file at the client machine at Venus. When a file is closed, if any writes were done to that file, then those writes are propagated to the Vice, which then updates its copy of the file. When a client opens a file, the Vice, of course, sends it the entire file, as we've discussed, but it also gives it a callback promise. The callback promise essentially is a promise that says that if another client modifies this file and then closes it, then a callback will be sent from Vice to this Venus. Okay, so essentially, if a particular client, Venus, has opened a file, it's given a callback promise that says that if another client opens, modifies, and then closes the file, then this client will be informed about that modification. Typically, the callback state that is maintained at Venus is only binary. It says that the state is either valid, or if the callback is actually done as a result of another client's updates, then that state is set to be cancelled, which means that essentially this Venus will then need to go and fetch the file again from the Vice daemon. Okay, so that wraps up our discussion of distributed file systems, which are very widely used today both in data centers and in smaller scale clusters. We've discussed the design of a vanilla distributed file system, as well as two very popular file systems, NFS and AFS. Now, this is only the tip of the iceberg, and there are many other file systems out there today, both cutting-edge research file systems as well as file systems that are in use today very widely in clusters and in data centers.